Today we are going to discuss on taphole management. Our goal is to maximize the plasmonas stability by reverse engineering 2 years of historical data. Instead of relying on gut feeling, we have defined exactly what a perfect hearth drainage campaign looks like. By the end of this talk, you will see the data-driven path to securing our furnace long-term health. So why does these matter? Because a 7000 TPD furnace operate in a delicate counter current regime. We must avoid the red zone. If taphole drainage fluctuate, liquid levels rise, which permanently damage burden flow and thermal deficiency in a big way. This leads to a clogged deadman, altered gas flow, and severe operational delays. Our objective is the green zone, maintaining an optimized drainage profile to protect the furnace structure and ensure production stays on the track. Now, historically, we have judged success by one metric, that is days in operation. But that's a flawed way to look at stability. Subjective practices often mask the root cause of the furnace instability. To fix this, we analyzed 2 years of continuous data across 4 taphole operating in tandem. Our mission was to build a quantitative model that finally removes the guesswork from casthouse preparation and taphole entry. So, to get a full picture, we do not just look at 1/2 number, we measure 16 distinct operational dimensions across the 4 categories. We track pacing and yield like drainage time and production, mud mechanics, especially clay injection, supposed to be very important, and deviation in it like the spool front not level, clay not going, clay property are not matching like extrusion, properties are bad, and so many things. As far as structural integrity is concerned, ensuring taphole length stay between 3.1 3.4 millimeter, that which also depends on the hearth dia, but mostly it taken as in general. And coming to the operational friction such as the tap interruption. So this comprehensive view ensure we are not sacrificing long-term integrity for short-term pacing. Not all metrics are equal. So we built a weighted scoring algorithm. We use filters to prioritize what actually harm the furnace. Coming to filter 1, which carries a 3 times weight for critical operational threat like closed furnace time, the hardest thing to control that causes the most severe harm. Filter 2, which focuses on the drainage and structural harm at a 2 times weightage, while filter 3 handles daily process control. So this 26-point system allows us to grade every campaign with total objectivity. So when we ran the numbers, the noise fell away and two outliner campaign emerged with an 85% success rate. Specifically, Taphole 2 campaign 13 becomes our definitive blueprint campaign. By grading against our 16 parameter engine, we could see exactly what these high performers were doing differently compared to the a reactive campaign that struggle to reach to 30 or 40% success. So let us discuss the consistency over duration. Here is the key takeaway. Campaign 13 achieved peak stability by prioritizing consistency over campaign duration. On the surface, it looked flawed because it ran for 31 days and 125 tap, both above our theoretical limits. However, the underlying data was perfect. It maintained an average drainage time of 181 minutes and consistent 3.1 meter taphole length. So this exceptional consistency in drainage cycle create unmatched hearth stability, overriding the risk of those extra days in operation. Though it looks simple, but this is the backbone. Now coming to our the slide which is on a success versus failure. As we can see, what what separate a blueprint campaign from a failure? And as you can see, the reactive campaigns are highly volatile, characterized by poor clay gun maintenance and short taps with a massive drainage discrepancy. In contrast, the blueprint campaign uses preventive sealing with a high extrusion clay for solid compaction. Most importantly, it relies on mechanical consistency driven by the steady, disciplined use of 55 millimeter drill bit. So now our coming to our deliverables for the success, which is very important slide. And to conclude, we are adopting three operational standards today to replicate this success. First, we will standardize the 55 millimeter drill to secure that ideal 181 minute drainage time. Second, we will institute proactive equipment maintenance, inspecting clay gun and drillers or drill guns or drill and mud guns before operation to prevent consecutive taps. Third, we will utilize immediate operational corrections. If mud volume is lacking, we correct it immediately upon opening to secure our 3 millimeter, that is 3 meter uh, or 3.1 meter length of taphole early. By following these deliverables, we ensure maximum stability for the campaign